Hi everyone, and thanks for attending my presentation. I'm Julien Lesouple, and I'm currently a postdoctorate at TESA Laboratory in Toulouse, France. My postdoctorate is funded by both Thales Alenia Space France and TESA Laboratory, and is about anomaly detection with user feedback. So today I will talk to you about incorporating user feedback into one-class support vector machines for anomaly detection. So first, I will give some context on this study. Then I will present you one class SVM. Then I will explain how to incorporate user feedback into one class SVM, which is the main contribution of this presentation. And finally, I will present the results on some experiments and give some conclusions. So as for the context, as you may know, there is an increasing interest for machine learning and artificial intelligence, mainly due to the evolutions of today's computers, which have high computation capacity and high memories, and also because there is an increasingly important amount of data due to the increasing number of sensors, and also because these sensors are cheaper, namely in the context of IoT. Machine learning is mainly used in regression, which is the prediction of a continuous value. So for instance, the prediction of the price of a house given its area, its number of rooms, etc. And also in classification, which is the estimation of a discrete value. So for instance, if you want to predict if a patient is healthy or not, given its ECG, its weight, its age, etc. Usually there are two phases in machine learning. So the first phase is a learning phase, where training data are fed to the algorithm to learn the prediction function, and a validation phase, where testing data are fed to the prediction functions computed in the first phase to validate the results. As for the learning phase, there are mainly two kinds. So you have on one side supervised learning, where the expected outputs are provided to the algorithm, and unsupervised learning, where the expected outputs are not fed to the algorithm. So anomaly detection is a special case of machine learning. It consists in a classification with two classes, so namely nominal data and anomalies. And usually the learning phase is unsupervised. The specificity of anomaly detection are that the data sets are very imbalanced, because you should have few anomalies in the data set. And sometimes training data may not even contain any anomaly. So the most common approaches during the learning phase are to assume that most of the data belong to the nominal class, and that nominal data should be gathered in a small subspace. Therefore, if there is an anomaly, it should be far from this data and far from the nominal data, and therefore far from the small subspace. So one particular algorithm of anomaly detection is the so-called one-class SVM, which relies on support vector machines. So the principle is to find an optimal hyperplane in a feature space, separating nominal data and anomalies. And moreover, you authorize at most a proportion of nu of the training data to be detected as anomalies. So this problem can be formulated as follows, which is a constraint optimization problem. The first term is to minimize the margin of the classifier. And the second term involves a so-called slack variable xi that will ensure that at most a proportion nu of the training data are detected as anomalies. Finally, this optimization problem is made under several constraints, ensuring that the algebraic distance between the training data and the estimated hyperplane are positive, except for those for which the slack variable are strictly positive. So this relies on support vector machine theory, and we can show that the solution depends only on a subset of the training data, which are the so-called support vectors. So as for the feature space, one can show that the solution only depends on the dot product phi of x on the dot product of the training data, and therefore there is no need to define explicitly the mapping phi, but only the dot products, and this consists in the kernel trick So we just have to define the function k here. There exist a lot of kernels, including the radial basis function that will be used in this presentation, which is also called the Gaussian kernel due to its expression here. And moreover, there exists a heuristic rule to determine the parameter of this kernel. Indeed, this kernel can be seen as a Gaussian function, and therefore gamma has the role of an inverse of a variance, which can be estimated robustly with the median of all the pairwise distances in the training dataset. So concretely, if you apply one class SVM to this synthetic dataset, so this is for a low value of nu. So as you can see, there are no training data outside the border. But when I increase the value of nu, I change the border to let more and more data outside the decision function. So a first observation here. So if we take this one class SVM here, let's imagine that the anomaly class is this cluster here in the center. We can see that it will never be detected using one class SVM. So this motivates, this is the first motivation to include some feedback into the anomaly detection. And moreover, if we have new training data outside the this boundary here, but they could consist in nominal data, we would like to tell the algorithm that this this data should not be outside the boundary. So now we shall see how to incorporate user feedback into one class SVM. So why using user feedback? It is complicated to label all the data sets because there are a huge number of data. And as we have just seen, unsupervised anomaly detection might lead to false alarm and misdetection. So the idea is to ask an expert to label only a subset of the training data. So there is already an existing approach, which is called active anomaly discovery, which tries to show in priority anomalies or the more ambiguous nominal data to the expert to get feedback for this data. So this gives an iterative algorithm where anomaly detection is initialized with an unsupervised algorithm. So for instance, it has been applied to isolation forests. And then there is a loop until a maximum number of queries to the expert has been reached. So in a loop, namely, you compute the scores for unlabeled data, and you send the data with the highest anomaly score to the expert for feedback, and you compute the new decision function. So the key here is how to compute this new decision function with the labeled and unlabeled data. So for active anomaly discovery, the authors propose a custom cost function which tries to be close to the original solution while taking into account the feedbacks. But here we propose to use one class SVM with labeled data. So what we propose is to take the one class SVM problem and to add some constraints depending on the labeled data. So for instance, we want to enforce labeled nominal data to have a positive distance to the hyperplane. And we want to impose to labeled anomalies to have a negative distance to the hyperplane. And we also add slack variables for labeled data to avoid overfitting. So if we go back to this synthetic data set here, we can let's imagine that the experts labeled this data as anomalies. Then the decision function will be modified according to this decision and let this unlabeled data inside and these labeled anomalies outside. If we go back to the second case where we have new nominal data that should be included in the inside the decision function, when we add the feedback using the proposed approach, we get this new boundary here. And of course, we can input both anomaly and new nominal data inside the algorithm to get this new boundary here. So in a nutshell, we just presented one class SVM with user feedback. So the algorithm is easy. So first we run one class SVM on a training data set, and then we alternate between query to the experts for the highest anomaly score and re-estimation of the border using the proposed algorithm. And we stop until a maximum number of queries has been reached. So now if we want to take a look at some experiments. So first, this is a 2D data set used in the AAD article. So on the top left, this is the solution for no iteration, so no feedbacks. So this is namely the one class SVM solution. And after there, we had some feedback. So here there are only one feedback, then 10, then 20s and 40s and 80. And as we can see, the boundary converges to this function here, letting a huge part of anomaly outside and the most part of nominal data inside. We also try to challenge this method on benchmark anomaly detection datasets. So here the purpose is to show the more anomaly to the expert, and therefore we plot the number of anomalies presented to the expert versus the number of data presented to the expert. So the optimal solution should be a straight line with slope 1 and passing through the origin. And as you can see, so for instance, this is the case for isolation forest here, but the main comparison, the main observation here is that in any case, so the injection of feedback allows to increase the performance of the unsupervised anomaly detection algorithm. And moreover, isolation forest and one class SVM with expert feedback seem to give equivalent results, except for these two data sets here, where the isolation forest with user feedback seems to be more optimal when using this criterion of showing the more anomalies to the experts. But as you can see here, for one class SVM, there is like a small period of initialization, and there we obtain a straight line with slope 1. So this means that at each iteration, an anomaly is shown to the experts. So now some conclusion. We presented one class SVM with partially labeled datasets, and we applied this algorithm to, we applied this problem to active anomaly discovery. So future works will consider other formulation for more interpretable hyperparameters. So as we've seen in the formulation, we added some hyperparameters in the cost function, but we don't have any insights on how they modify the cost function. So future work will try to better explain the hyperparameters. Then we will see how active anomaly discovery can be seen as a support vector machine problem, and therefore can be applied to both one class SVM and isolation forest. Also, future works will try to be more to challenge the various methods to other metrics than the one presented in this article. So thanks for attending my presentation. And if you have any question, I'll be very glad to answer them. Thank you.